This brings us now to Chapter 6, where we're going to talk about a lot more about the pointers. So the first thing we're going to talk about in a little bit more detail is the address operator, which is an ampersand symbol shown right here. And we've already been using that when you do a scanf function and you get something from the keyboard and you store it in a place called X. So what this actually means that you're reading the value from the keyboard and you're storing it at the address that is specified or identified by X. So you're storing this in an address at that point. So I have a piece of code now. Here is a simple, this is similar to the first example in Chapter 6. This code is going to demonstrate what's happening at addresses. So I could get the character from the keyboard and store it in a location X, but how about if I just say I'm going to have an asterisk stored in a location called A and a number 2 stored in a location by B. Notice that I've called B a character, so I'm storing the character 2 in the location of B. And then I have two printf statements here. And so I'm going to print A, and then I'm going to print the address of A. So the address operator indicates that I'm going to actually print its location in memory. And same thing with B. The format specifiers here, I have a %x shown. %x means that it's going to show the answer or the address in hexadecimal. And the %u means it's going to show the address in an unsigned int. So let's run this program. Let me clear for a moment. Clear. Actually, I'm going to run it with the debugging option. No, I think I'll do that on the next problem. So this is example 6_1-0. Fine. All good, yes. So when I run it here, it does show me that A had the value of an asterisk, but the address of A is in hexadecimal, so the first one was in hexadecimal, and B, which was the character 2, which has an ASCII value of 50 or 50, that's in decimal numbering system. B has an address of this number, which I outputted as an unsigned int, so you're getting it in a base 10 or a decimal number. I could have outputted that as a hexadecimal value if I wanted. So let's go back to our program. So this indeed shows that the value stored at A is different than the address of A. It is worthwhile for us to show you that in memory, but I'm going to do it on the next program, the next example coming up, because we're going to talk about pointers now. So pointers are a variable that can store addresses. Here is my example piece of code. I've declared it an int, I've called it number, and the value stored at the location specified by number is going to be the number 99. And then I have this use of a pointer right here, and that says the value of the variable p number, so is an address, and it's the address of number. So this is what's happening in memory here, charted on the right. So perhaps number gets stored at address in hexadecimal with a bunch of leading zeros here not shown, but perhaps number gets stored at this memory location. And you can see the value stored there will be 99, and the address in memory will be here. And then at some other address, this address, for example, the value of p number is stored. But p number stores an address. So p number stored the address of number. So we say at this, we say that p number points to this address. So that's why it's called a pointer. So declaring pointers, you have to declare a pointer with the same data type as the variable to which it points, because the compiler has to know how much memory is occupied to the variable that it's pointing to. So, for example, a short integer only takes up 2 bytes of memory. An unsigned short integer also takes 2 bytes. It's just that the range of numbers that you can display is different. A character, is character on here? Yeah, character only takes 1 byte of memory to store. Actually, you can see with this piece of code here, you can see how much memory each data type takes to store it in your memory on your computer. So we use the size of function, which is included in the standard I/O library, and you say size of character, for example, and it gives the answer in the number of bytes it takes to store a character. So a character takes 1 byte, an int takes 4 bytes, a double takes 8 bytes, a long double takes 16 bytes. So remember when we were doing factorials, I suggested that you use a data type of long, because the numbers get very large and you want to be able to store those very large numbers. Declaring pointers. So like I said, you must declare the pointer with the appropriate data type. So for example, if I declare this pointer int and the dereferencer, which is the asterisk p number, then I know I'm pointing to, I know that the address stored by p number will point to the address of some integer. So one of the things, though, to be aware of, that you always have to initialize your pointers. Uninitialized pointers are hazardous to your program. If you don't know yet what value your pointer should have, you can initialize it to null. It doesn't point to anything, but then it's safe because it does have initialized value of null, and it reserves the space in memory. So if you do this, you're not necessarily reserving the space consistently in memory like you may want to do. So I'm more on this example right here. Here I've declared an int called number, and I'm storing in that location the number 99, and then this statement right here says that I'm making a variable called p number, and it's going to hold the address, this address right here, which is the address of number, so it points to the address of number. You must declare the thing that's being pointed to before you declare the pointer. So the declaration of number must precede the declaration of the pointer that stores the address. If you don't do this, the code won't compile and you'll get some kind of a compiler error. So now I'm going to do a more interesting example, and I'm going to do it with the, I'm going to disassemble it. I'm also going to run the debugger, and I'm going to show you what's happening in memory, because I really want you to get the concept of what the dereferencer, the asterisk does, and what the address operator does, and what pointers are doing. So this is not a complex program. All I'm doing is I'm declaring a variable called number, and I'm going to give it the value of 10. So it's 10 in decimal, but I can, interestingly enough, write it in hex if I want, by preceding with a 0x and then writing in A. A is the number 10 in hexadecimal. I'm still wondering how many of you know hexadecimal. I know a lot of you do. I think I better just ask you, maybe take a poll to see if you know the hexadecimal, which is counting in base 16. So for example, you would say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you can't say 10. You need a new character, so you say A, B, C, D, E, F. And now you've counted to 15, and the next number would be 1, 0. I'll write that down here in a moment. Okay, so this is what my program does. I just declare one variable called number. I've initialized it to 10, which is A in hexadecimal, and I'll go ahead and print out that address, the address of where number is stored. And notice I have used yet one more format specifier. That a P actually means that it's an address or a pointer. So before I did X to do hexadecimal, this is going to give you the same result, but technically this is more correct. And then I'm going to output the value just to show you that it's a number 10. The next part of my code is I'm going to store the address of number. So this is the address of number right here. And I'm going to store it in P number. So P number will become a pointer. And then I'm going to show you what happens. So I'll say P number's address is, and I'll show it to you, and I'll show it to you in memory too. And we'll write down what these addresses are and show how they relate to each other. For the fun of it, I'm going to tell you what P number's size is by using the size of function. It will return how many bytes P number is. And then what P number's value is. So in this case it should be an address because P number is a variable that stores an address, so the value of P number should be an address. And this use of the dereferencer is going to show you what the value is that P number is pointing to. So let me compile it and show it to you. I'm going to compile it with the debugger option. So just for the front of it, let's just make sure it runs correctly and I have nothing unexpected. No problem. So it says right here that number's address is right here. This is a hexadecimal value. Number's value is a 10. Remember, I actually put it in hex as 0. I wrote 0xa, which is 10 in decimal. And then I say P number's address is this. So P number's address is different address than number's address. But what do I store at P number's address? P number's value down here, it says what I'm storing at P number's address. I am storing this, right? Which is the value, which is the address of where number is stored. So P number's value is this. That's where number is stored. And then if I use the asterisk, I can say what value it's being pointed to. This is called the asterisk is called the dereferencer. So okay, fine, well and dandy. Let's show that to you in memory and let's draw a picture so it makes sense. So I'm going to run the debugger, gdb, on this program. So there it starts. The first thing I like to do is I just like to see that my program's there. I like to see the line numbers in case I want to put a break in the program somewhere. I also like that while I'm looking here I can look at the program. So it looks like there's 27 lines of code in this program. There it is in the listing. Now I want to know where the program starts, so I'm just going to say break at line 1. So that's a B space 1. And it says my program starts at this address right here. So that's nice. I know where the program starts. You know, for the fun of it, I can disassemble the program if I want, just to show it to you, but that's actually not what we're going to focus on today, or in this lecture. If I do a /R, I can look at the whole thing disassembled in memory. So there's the whole program disassembled. I see the C code gets converted to hexadecimal right here, and then we can associate some mnemonics with these hexadecimal values, which makes it supposedly more human readable. But if I look carefully, I see a few things pop out. There's a main function. There's a printf function, so that's a function call going off somewhere in memory. And so you can sort of identify a few things. You can identify more if you know assembly language. Looks like I haven't displayed the whole thing. It says press return to see the whole thing. So there's the rest of the program. And of course you have finally something that ends the program there. So you can see how many bytes I take up in memory for your program, where your source code resides. It resides between this address to this ending address. We can see how many bytes that is, but this is actually the byte count right here. So each line that I've shown, is it the byte count? Yeah, it is the byte count, because this is 1 byte here. This is 3 more bytes, so we're at 4 bytes. So you can actually see that I took 166 bytes of memory to store this source code. So okay, well that's fine, I guess. So the other thing we can do is run the program in the debugger. Run. So you just say run, and it starts running the program. And the way this works is we're at some address now. The first breakpoint gets executed. We execute the first part of the program, which was scrolling back up. These comments don't do anything. These comments have no meaning at all in terms of what's executing and what we're seeing. And so I set the breakpoint at the beginning. I did run. It executed all of this right here, and it stops right here, right before it's going to execute this next line of code, and that's where it's sitting right now. So one of the interesting things that you can do right now is you could stop and look at what's in the registers. You could stop and see what's executing, but we don't need to do that right now. So let's execute one line at a time. Next. Next one is a printf statement. So let's execute that printf statement. And it actually executes that line of code and does what it says to do. And so when I said printf that the number's address is, it did it, and it showed it to me. It showed me that result. So you can step through your code one line at a time and see what's happening. This is a useful debugging tool, for example, if you're in a loop, and you can step through it one line at a time and watch it execute and watch it where it's going too. This program doesn't have loops, so it's not too exciting. Oops. So at this point in executing the program, I can actually show you in memory that the number A in hexadecimal or 10 in decimal is stored at this location in memory. It's not showing you all 64 bits, but that's okay. We know that there are leading zeros here, but I'm going to show you a new command. It's the examine command, which starts with an X. So you say X/ and then you have some options for using this examine command. There is a nice web page, which I will paste this into the PowerPoint so you can have it. But there is a nice web page that describes the use of this examine command for examining your memory. One of the things is your program has to be actively running to see these locations in memory. If your program isn't running anymore, you can't, the memory is no longer valid for the program. So here's the format. It's X for examine, and then / and then there's some options over here, or you could just say examine a certain address. But the options are useful. The options say N is how much of how much you want to display. I'll show you what I mean. And the display format and the size of the unit. So if I want to display 10 bytes, I would say this is a 10 and U is B for bytes. You can display your format. These are your two options. It looks like S or I, or hexadecimal is an option. So I'm going to display it in hexadecimal because this is what we're interested in, is looking at the contents. If I explain it, if I don't put this hexadecimal in, sometimes it interprets the hexadecimal and it looks kind of cryptic and we're not really getting the information. So there are some choices here. You can display 10 bytes, for example. You can You can display half words, which are 2 bytes. Words are considered 4 bytes, and giant words are 8 bytes. I actually like giant words for this, and I'll show you. And then the address, and this is a GDB function. So let me show you. So I am going to examine 1 giant byte in hexadecimal at this address. So let's look at what's happening at that address. So 1 giant byte in hexadecimal. Oops. And I want it to be a giant byte, 8 bits long, right? And the address I want is numbers address. So here is numbers address, and the part that the program wasn't telling us is all of this leading part. It wasn't all zeros, but you can see at the end of number, this actually might be something else. Well, no, this is the full address, but you can see that at our address of interest we have the OA, which is the decimal value of 10. So I'm going to run the next step in the program just to remind you of what the next step of the program is. We just did this. We stored this number in address. We stored A in number. We printed A's address. We printed A's value. So that's where we are at in the program right now. The next part, when I execute it in the debugger, is that I'm going to store the address of number in P number. So let's look at that. So next is a print statement. Okay, so I printed that out. This is my next line of code waiting to be executed. Let's do it. Next. Let's do the 2 print statements for the fun of it. Doesn't matter. Next. Actually, we'll show them all. Okay, so my program's still running. It's waiting for this get character. I don't want to execute the get character yet, because if I do, then I can't look at memory anymore. So examine. I'm going to look at 1 giant byte. Let's do it differently. Let's look at 4 bytes, because an integer is stored there, right? And an integer takes 4 bytes. Let's look at 4 bytes. Look at it in hexadecimal, and look at it as bytes. And let's look at P numbers value, right? At P numbers address. Oh, that's P numbers value. I want P numbers address. P numbers address. Printf. P numbers address is, do it, P numbers address right there. P numbers address. So the display is a little bit different, but at P numbers address we see the value ACCA2300. Is it 00? So at P numbers address we see, oh, it's in, we got to watch for that. The order is important here. Let me try that one more time. So it actually displays in the order is reversed from what you think it should be. So I can see that right now, because P numbers address is here. So there's P numbers address, and the value stored at P numbers address is here. The order isn't what you would expect. So the value stored is 23CAAC. There it is, the value of P numbers address. So I don't quite like the way it's displaying, because it's confusing to see it in backwards order. So let's do it as a word. 1x word. There we go. I like it seeing it that way. Now we can truly see what's displayed. So at this address, we have this value, and this is P number's address, and it's storing the address of where number is. So maybe this is confusing looking at it in the debugger. So I would rather, maybe we should do it showing it as a picture, because sometimes looking at who's pointing to what makes it more, makes it sink in better. So if you seem confused right now, that's okay. Every time pointers are introduced in a programming class, people are confused for a while, and you keep working with it, and then all of a sudden it will click. Trust me, all of a sudden it will click. So let's look at the program we had here for a moment ago. It was this one. Let me put it in PowerPoint so we can look at it a little bit better and make a drawing that goes with this. That's what I want to do, is show you how the pointers work. So, sorry, creating a slide on the fly here. So here's the program. Let's write down what the results were each time, and we'll draw in a picture that's useful sometimes for people to understand pointers. So so this is the value stored at P number, right? Let me just shrink this a little bit, or at number. So this is what we did. We had a value called number that we declared, and then we said, where is number stored? So we found out that number is stored at this address using that command. And if I go back here and I look at my program, actually I'm going to exit out of this. So if I want to quit, I just say quit. Oh, it's still running. Do you want to kill it? Yes, I do. So run the program. Okay. These were the results that we got. But it's useful to see it drawn out. So this address 23CAA0 occurs before 23CAAC, because if we're counting in hexadecimal, it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, not 10, but A, B, C, D, E, F, and then it goes 1, 0. So at this address, which would be, here's an address, 23CAA0, there's an address, and the question is, what's stored in that address? And this is 23CAA1, this is 23CAA2, ... and down here is the address 23CAAC. So I've gone down where the last digit was a 0 to where the last digit is a C in memory. So what is stored at 23CAA0? It says P number's address is stored there. So what is P number's address? Let me pull that back up. One more thing that I need. I needed this. Okay, so things that we're looking at here. Draw a picture of what's happening, because sometimes it's harder to look at the what's happening in memory. So number's address. Number's address is here. Number's address is here. This is where number is. Number is here, and the value stored there is a 10. So 10 is actually A. And if I look at it in memory, I will have seen that there was an A stored there. P number's address is right here. P number's size is 8 bytes long. So we know that it's 8 bytes long. The size of the thing it's pointing to is 8 bytes long. So it takes 8 bytes to store here. P number's value is 0x23CAAC. Oh, CAAC. That's what's stored there. What is that value? That's the address of here. So P number is pointing to there. The value that it's pointing to, if I dereference it, the value that it's pointing to is a 10. Right? That's a 10. 10 in base 10 equals A in hexadecimal. Okay, right? So number is stored at this location right here. The value of number is A, or 10. P number is stored at this memory location right here. The value of P number is an address. This address points to that value over here. So I went back in the debugger just to show you one more piece of information that's the same thing that I just showed you pictorially on the slide. So I'm saying examine 4 words in hexadecimal at that beginning address, which is, I'm going to start at this address right here, and I am going to examine the memory at these addresses up to where this is stored at 23CAAC. So I go back, I look at the memory. I had to play with this for a moment, but now I can show you. So there's the starting address of where I'm doing an examine. Examine 4 hexadecimal words beginning at this address. So that's what I did. There's the first word, and stored at this address is this value, which is the address of number. And then later at this address is where number is stored, but we can count up to where that address is. So that address is this one right here, but you have to count it up in bytes. So there are 4 bytes, 0, 1, 0, 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8, 9, 10, 11, and to that address here. So anyway, that's where it's stored. Show you that more carefully. This is 0, 1, 2, 3. So AC right here is 23CAA0 address. This is the 1 address. This is the 2 address. 3, 4, 5. This is 4, 5, 6, 7, 8, 9, 10, 11, and this is address 12, which is this is what's stored in address 23CAAC. So address that ends in C is stored right here, and this is what's stored right there. Maybe that's worth clipping and drawing so I can show that completely to you. So let's clip that. You can have it back as a reference on how to show the memory and what's happening in the memory. So it's associated with this picture right here. So it is actually drawn out a little bit bigger here for you, and I'll label out the addresses so you can see. So my command here said show it said to, that was examine for hexadecimal words, and a word is 4 bytes. So this is a word, this is a word, this is a word, and this is a word. So I've examined 4 words starting at this address right here. So let me change color so that you can see better. This is a byte right here. So that byte is stored at address 23CAA0. So what's stored there? AC is stored there. This right there, this next byte is stored at address 0x223CAA1. That byte is stored there at that next address, which happens to be a CA is stored there. This is the next byte. This next byte is at address 0x23CAA2. And then this next byte is at address 0x23CAA3. So that makes this one be at 4, 5, 6, 7, 8, 9, 10, 11. And that makes this guy be, this byte right here, this byte is at address 0x23CAA3. And a C is the number 12 in binary, but in hexadecimal it's a C. So that was 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, not 10, A, B, and address C is right there. So, okay. So this is where, going back one slide, we saw that at address ending in 0, we have stored another address, and that another address is this address. So it points to this location right here, and stored there is the number 10. So far you probably think, why use pointers? Because you can do it another way. So I'm going to show you one very common way, or one very common reason why you might want to use a pointer. So consider this program here. I have 2 variables that I've declared, C and D, and C has a value of 3 stored in memory, and D has a value of 5. And I want to swap that. I want C to get 5 and D to get 3, and I want a function to do that. So we had sort of looked at this at one point earlier, but if I write this function like that, then I want to swap 2 values. I'm going to pass 2 integers to this program, this function, and I'm going to create a swap function. By the way, if I was not in a function, this would work, but I'm in a function, so things are only in existence locally while the function is executing. So I bring in the value of A, I put it in temp, then I overwrite A with the value of B, and then I give B back the value of A, and the value of A and B are swapped within this function. But they are not swapped where they are stored in memory somewhere outside. They only got swapped within this function. And maybe you have to call a swap function many times in your program, so it needs to be a function. You need to not do the swap within the main body of your function. So no matter how you try it, this will not work. And I will even show you that this will not work. I forgot what version I was on, so I'll go ahead and compile it. So I will show you that no matter how you look at it, this program will not work. So C did stay being 3 and D did stay being 5. It did not swap at all, even though I created the function to swap it. I called the function. I wanted to swap my variables c and d, so they don't have to be named the same as the function, the locally defined function variables. So I wanted to swap 3 and 5, and it did not work. I printed that to show that. So this is where pointers become very, very useful. So one thing I can do here is make this now a pointer. So I'm going to pass in, I'm going to use a location that's pointed to, the location of A, or point to A. And so we'll do the same up here in my function declaration. So I need to finish that out through here. These are all pointers. But what happens here, at this step right here, is that the location that A points to is what's getting swapped. It'll go out to the memory location where these variables are, in whichever case, whatever one I pass in there, and it will work on what's contained at those memory locations. So I've used the dereferencer so that when I go to the location that I'm pointing to, it's going to be the content of that location. So this almost is correct at this point in time, but the last thing that we need to make sure is we swap their addresses to here. So we will go ahead and do that with the address operator. So this should work right now. Let's try it again. This is a really actually common application, doing a swap. So recompile it, run it, and yes, indeed, it does work. So it actually goes to the location where my variable is stored, where C is stored, gets the content of C, and it changes to what's stored at these memory locations. So this is a program very much worth you spending some time studying it and seeing exactly what's happening, or draw a picture to go with this program so that you can see what's happening on the program. So I added a few notes to the program, even though you should walk through this yourself and make sure that you understand. So when I'm called the function swap, I'm swapping what's at C's location, right, because that's at the address operator, with what's at D's location. And so if I assume like C is stored at some location, the contents of it is 3, and if D is stored at some other location and its contents are 5. So I'm saying swap what's stored at C's location with what's stored at D's location. So now I go down here and I look at the actual function that we created, and what this means right here, means the contents at some address. So I'm swapping I'm going to swap some contents at a particular address. And what do I pass in? I passed in an address right here. So I pass in an address, but I'm going to get the contents of what's at that address right here. So the thing that I'm pointing to. So the contents of the address go in temp. The contents of this address go right here, and the contents get swapped. So worthwhile. Continue to study that program. Okay, this YouTube is long enough.